Group 6, the physics group.
The science guy.
The problem that was investigated was, what would happen to the rate of diffusion if concentration was varied among the bead samples? Diffusion was defined as the movement of a particle down its concentration gradient, which means motion from high to low concentration of that particle.
The hypothesis was stated as increasing the concentration of the particles in a sample will increase the number of collisions and overall movement of the beads, causing an increase in average velocity.
Varying concentrations of equal mass silica beads were compared to each other in water. An emphasis on the bead's motion in a two-dimensional plane was observed. It was found that the result of increasing concentrations of silica bead was an increase in the average velocity of the beads, so the hypothesis was supported.
Diffusion was modeled using 1D collision simulation in Python. For objects with the same mass and different velocities, a head-on collision will result in an exchange of the initial velocities. In diffusion, the velocity of two particles is exchanged between the other same-sized beads and the water molecules. In this lab, beads can model proteins moving through a cell's cytosol. However, in a cell, proteins are much larger than water molecules. In the case of this lab, a water molecule is about 2.75 times 10 to the negative 10 meters wide, and our silica beads are 1.5 times 10 to the negative 6 meters, over 5,000 times larger. This would mean that the transfer of momentum from beads to water molecules is almost negligible in comparison to bead momentum transfer. These repeated collisions will make the beads appear to have random motion as they diffuse. Eventually, the beads will settle, and the samples are only colloids. In a cell, settling doesn't occur as the biological processes in an organism keep particles in constant motion.
A good way of explaining this concept is by using Newton's second law of motion. This law states that the same mass objects will conserve momentum by exchanging their velocities. The equation for the conservation of momentum is shown here on the screen. When the collision occurs, the masses of the involved particles will remain constant. It is the velocities that will transfer from one particle to the other, resulting in the conservation of momentum as our model shows. It was predicted that as the concentration of a sample increases, there will also be an increase in the rapidity of collisions between the particles. The more collisions result in maintaining a higher average velocity, as well as a higher rate of diffusion. Each sample of silica beads is expected to have a gradually decreasing average velocity among particles as they settle, but the variation in collision rate will ultimately have an impact on this settling pattern.
The independent variable that was studied was concentration of the particles. The dependent variable was the average velocity of the particles. The first step of the procedure was 3 silica beads of mass 1.5 microns with various concentrations were prepared. It was a 0.5 times concentration, 1 times concentration, and a 10 times concentration. Then 10 milliliters of each sample were placed on a slide to be viewed under the microscope. Each sample was recorded on video for 10 seconds from the time it was placed under the lens before any substantial settling took place. 3 beads at each concentration were observed with tracker to record average distance traveled and average velocity. Between trials, the glass slide was cleaned and the objective lens was refocused to the next concentration of silica beads.
Just like in any other physics problem, there were assumptions that had to be made. In this lab, there were 3 main ones. The first was that all ejection rates were the same for each trial. The second was that each slide had an equal surface area of sample while under the microscope. And the third was that more concentrated samples have less distance between the particles.
A video of roughly 9.5 seconds was analyzed for each silica bead concentration using the program tracker. The x and y coordinates for 3 distinct particles were tracked at time intervals of 0.53 seconds, adding up to 18 data points per particle per sample. In a spreadsheet, the distance traveled by each particle between frames was calculated, which was always positive from using the Pythagorean theorem. Next, the average velocity, or speed as they were all positive, was calculated. Line graphs display the varying speeds of each sampled particle as they diffuse in the sample over time. A scatter plot compares the average velocity of each of the 9 sampled particles compared to the concentration of the sample they came from.
Establishing a frame of reference is not necessary in this situation because the data necessary for this hypothesis is based off the magnitude of the velocity or the speed.
As this data shows, the average velocity increases with increasing concentration. Linking this to colliding particles, the graphs showing the changing velocities support the prediction that frequent collisions lead to frequent transfers of momentum. The up and down pattern of the graphs shows the give and take nature of diffusing particles. As not all particles move at the same speed during diffusion, not even at equilibrium.
There were several sources of potential error in this lab. First, a medicine dropper was used to eject the sample onto the microscope lens. A medicine dropper isn't a very precise measuring instrument, so the ejection rate and amount could have varied among the trials. Also, only a limited number of particles could be sampled with tracker since the depth of the sample on the slide could not be fully realized by the fixed focus of the microscope. Only particles that remained in focus in the video for the full 10 seconds were candidates for being tracked.